Okay, more properties of the definite integral. I guess we're going into a part 2 here. As we've talked about the definite integral, if we take the limit of our Riemann sum, if we did 6 rectangles, 20, 100, 2,000, and finally an infinite number, if we did an infinite, we'd get the true area under the curve. And then now we're talking about this definite integral, and we're looking at some properties that you need to know on page 307 and beyond. I'll just list some of these here. You can go to your book and make a better copy if you want, but here is we're going to integrate from a to b of f of x dx, okay? And that is equal to, happens to be if equal to negative the value, if we just switch the limits, if we integrated what we might refer to as backwards. If we integrated backwards from b to a instead of from a to b, we'd incur this negative sign. Okay, so that's one property. Second property might be if you integrate over an integral the same. This might be pretty obvious, but if the interval is 0 width, if I want to integrate from a to a, if f of x dx, the area under that curve, be it positive or negative, would be 0. See, I'm catching myself. I say negative area. What does that mean? Again, I showed you before that finding area is not the same thing as integration. But we can use the idea, the concept, to find the definite integral. And we will do that in some problems. Okay, here's another one here. Say I integrate the constant c dx from a to b. This one I can give you a little picture of. If I want to go from a to b, and I'm integrating, let's see, say this, let's go black here, this function c, well, I bet you can tell me what that's equal to, right? That's going to be a rectangle whose width is b minus a, and whose height is c. Okay. 4 here then, some more of these. If I integrate two functions, a to b, f of x plus g of x dx, it's a linear thing, meaning if I add up all the f of x's and I add up all the g of x's, I could split this integral and just, I could find the integral of f of x dx plus the integral from a to b of g of x dx. And the same thing if you scale. If I want to scale a function, c, say I multiply a function by c, well, what does that do to the area and the negative area? It's just going to multiply. I can pull that c out front. I can pull the c out front. That's just a constant. C is a constant times the integral, okay? So this constant scales the function. It just scales the height, so I could pull it out. I could factor it out and so forth. Okay, maybe another. We got to use these functions like all properties. Listing them doesn't do you much good. Well, I mean, you got to see them here. And maybe this is really the last one I'll look at. I'll give you a picture of this. This one here is, say I wanted to integrate from a to c. A to c function of x. This could be equal to the function from a to b of f of x plus the integral from b to c of f of x. And I'm trying to see, oh, they put c in between. Okay. All right, I'm going to put B in between. You can see how they did it in the book. I put C, and I'll draw my picture here. And I put B in the middle and C here, and this might be A. So I could find A to C is basically going to be what? It's going to be this area here minus the red area here, because this is below the line. All right, and that could, so the integral from A to C would be the blue area minus the red area. It could also be, though, equal to, I can break up my integral, and I could integrate, say, from A to B, and I could say, well, this area in black, this is the black area here. Okay, and then from B to C would be what area? Well, that's maybe the green. The green would be this positive minus the red. Okay, so this would be the green. So I can break up my integral into intervals, okay? And I would do this. I didn't break it up in a very smart way here, because if I was smart, I would have broken my integral right at the point where it changes from positive to negative, and I could find the area above the curve was the value from A to B, and then I'd find this area from B to C, and whatever I found that integral, or the area, I would make it negative, and then I could say a positive area minus. But it would also work this way. I could cut it. I can cut any interval A to C into A to B plus B to C. Okay, I think we need to work. Let's work a homework problem. You've got the idea of the definite integral. We've given you the properties. Let's work a problem. Okay, the first homework problem we'll encounter will be dealing with this this particular function. And if you see, this function is defined as a piecewise curve, so we can kind of easily have an area interpretation. We can use geometric shapes in order to calculate what the integral, what the definite integral is. And one of the problems would be they wanted to know from 0 to 54, integrate that f of x dx. That's a dx, okay? So we take the height of this, and the first thing we might do, well, we look at this a little bit. It looks like everyone is 6. That's 6, 12. B is 24. C is 36, 48. They want to go out to 54, which is right here. Okay? So let's do the hard part of this first, and I guess, let's see. If I'm going out there, the first little shape I'm going to create shapes under the curve here. I'm going to get that as my A1. Okay. And this little rectangle I'll call A2. Here I got a triangle here, right? A3. A3 is going to go like from here up to there. Now notice these are all positive areas, so that's going to be A1, A2, and A3. That's going to be the integral from 0 to B is 24. That must be 30. This is 30. Okay, now if I want to go all the way out to that point, I've got a triangle right here. And notice now I've cut it such that that's A4, in case you can't read that. A4 is beneath the x-axis. It's going to be negative. And then this A5 is going to be a trapezoid. So anyway, let's calculate these. I'm going to say A1, a trapezoid is going to be the average of the heights, which looks like it's going to be, that's 6 here, 12, 18. This is going to be 6 plus 18 divided by 2. That's the average of the heights times the width, which is 12. So that trapezoidal A1 here looks like it's going to be 6 times 24. I'm saying that's 144. Okay, what's A2? Well, A2 is just a rectangle of height 6. 18 is going to be 18 times 6. 18 times 6 equals 108. Okay, how about this A3 now? A3 is a triangle. So it's going to be 1/2 the height, which is 18, times the width is 12. That looks like it's also going to be 108. Okay? So you can see this whole problem is going to fall apart pretty quickly. Let's look at A4 though. A4, another trapezoid. No, it's a triangle, and the height is 18, and it's 12. 1/2 of that. It looks like, it's exactly. We could actually see A4 and A3 are going to cancel each other eventually, but let's just tell you what the area is. A4, A5, oh gosh, so this all cancels. I can see the answer already is A2. The answer is 108. But let's do it the hard way. First, A5 is equal to the same trapezoid. Let's see, it's 18. It's 1/2. Oh no, I take that back. That's not going to be the answer because A5 is a little bigger than A1. It's going to be 18 times 24. Uh-oh, sorry, that's wrong. That is wrong. It's the average of those two. It's going to be 1/2 18 plus 24. The averages of the height between here and here times the width is 12. That's going to be 6 times 42. 3242, which to me is like 240, 252. Okay, so this integral now, well, what is the integral? Well, it's going to be A1 plus A2 plus A3. Now, A4 I have to subtract because it's beneath the line, right? A4 is beneath the x-axis here, right? This is all, so this is negative. Black, I guess it should have made red was negative and black would be positive, but that's negative minus A5. Okay, so the integral from 0 to 54 should be what? Well, A4, notice A4 and A2 are exactly the same. That's going to cancel with that. No, not A2. No, well, it's A3 really. Let's go back. These are the same shapes. A3 and A4, these cancel. A1 and A2, if you add those together, you're going to get 252. Oh my gosh. Okay, so this looks like A1 and A2, 144 plus 108 minus 252. Well, guess what, folks? That looks to me like it's equal to 0. So what we've just found is that the area beneath the curve, this area and this area, are exactly the same unless I made a mistake. A little different shape, but the positive area and the negative area are the same such that the integral itself is equal to 0. But look at what we've done. We're going to calculate these geometric shapes and use an interpretation of positive and negative area in order to calculate the definite integral. Okay, I think we can do our homework now, and next we will get into, after we finish the homework on this section, we will look at the fundamental theorem of calculus. Okay, see you soon.